All right, here is quiz number 2. We're going to go through the solutions. On part A, we say carbon forms two isotopes, carbon-12, carbon-14, and we want to determine which occurs the most abundantly, and there's a reference to the periodic table. So how does a periodic table relate to carbon-12 and carbon-14? So let's look at the periodic table. We get the reference for carbon, and we see the following, right? We see carbon, 6, that's the number of protons, 12.01. What does this mean, right? This comes from the periodic table, and what is the significance? This is the atomic mass, and what that means is that this is the average mass of all the carbons, right? In the universe, theoretically, to the best of our knowledge, right? The mass of all the carbons. And by just looking at this average mass, which is 12.01 atomic mass units, we can understand what the most common isotope might be. So let's say we have these two naturally occurring isotopes, carbon-12, carbon-14. The average is 12.01. We know that carbon-12 has a mass of 12 atomic mass units. It's actually by definition, so it's exactly 12. And carbon-14 has 14 protons and neutrons, so roughly an atomic mass of 14. Therefore, if the average is 12.01 atomic mass units, we know that carbon-12 must be more abundant because the average is much, much closer to the mass of carbon-12 than of carbon-14. And that's part A. On part B, we see, well, on a faraway planet, we have a different atomic mass. So the 12.01 atomic mass units, that's not going to apply if we constrict our view to just this planet. And here, carbon-12 occurs with an abundance that's a certain amount, and carbon-14 is the only other species. We want to calculate the atomic mass of carbon on this planet. So how do we approach this, right? This is very much like the problem before, except we're actually being asked to calculate the average. So how do we calculate the average based on the percentages of these species? So here we need a weighted average, and note that it's two different species that are the only ones that contribute to this average, the carbon-12 and the carbon-14, which I'll just call C12, C14. The average, if these are the two species that are available, is going to be the fraction that's C12 multiplied by the mass of C12 plus the fraction of C14 multiplied by the mass of C14, which basically says that if it's 10% of a certain mass, you need to multiply that mass by 10%. And if it's 90% of the other, you multiply that mass by 90%. And that's how we weight the different contributors to the average based on their prevalence. So this is the formula that we want to use. If we had 3 or 4 or 5 or any number of species that are contributing to the mass, we would have that many terms. Here we just have the two terms. There's the C12 term and then the C14 term, with fraction times the mass being what I'll refer to here as the term for that contributor to the average. So one thing that I really recommend is, we have our formula, but go ahead and get all of your variables, including their units, listed out on the side. Because once you do that, you can kind of just plug in, and then when we're actually in the math itself, we don't really need to put all the units because that can really bog down our ability to see the mathematics. And we actually have all of the units that we're keeping track of in a little sidebar. So I think that's a great practice. We can see the fraction of C12 is 88%. The fraction of C14 being the only other species must be 12%, 12.000, based on the significant figures we've already been given. Mass of C12 is 12 exactly, and the mass of C14 is as given in this problem as well. The average we don't know, and this can help you keep your variables organized so that you can determine your unknowns too. If we do all this successfully, we plug it in, and it's all downhill from here, and we get 12.240 atomic mass units, 5 significant figures based off of the percentage data, which is given to 5 significant figures. Notably, when we're putting in our fractions for the average, we can't have it in terms of a percent. We have to have it in terms of a decimal. Note that 88% literally means 88 divided by 100, which gives you 0.88. All right, here on the next part of the quiz, we have part C, which says state the chemical formulas, and you can consult this table of polyatomic ions. Note that these starred ones are ones that I think are the most common and should be probably committed to memory by now, but you have it here. Definitely something that will help moving forward. So as we look at all of these names on the right side, the first question we should ask ourselves is, are they ionic or covalent? Each of these different compounds will be either ionic or covalent. So let's go through all of them and keep in mind that the best way to determine if something's ionic or covalent is to see if it has a cation, a positive ion. Most of the time a metal, but could be a positive polyatomic ion, as in the case of ammonium phosphate. This is really the only cation that's going to form compounds. H3O plus, hydronium, very important when considering acids and bases, but doesn't really act as a cation in an ionic compound. Magnesium hydroxide, we look at this. I see magnesium. I say that's a metal. It likes to form +2 ions. That's a cation, must be ionic. Lead 2, this is in reference to the lead 2 plus cation, so ionic again. Phosphorus pentafluoride, we look at these and I look at the periodic table and I see, well, fluoride is a nonmetal, phosphorus is a nonmetal. So I'm not seeing anything that's going to act as a cation in this compound, and therefore this one is actually covalent. Sodium nitrite, I see sodium, Na+, that's a cation, so it must be ionic. And carbon monoxide, for the same reasons as phosphorus pentafluoride, I see no cation and therefore also covalent. Okay, so I think that's a great way to break things down. Let's just deal with the ionic ones next, because those are, I think, arguably a little bit more complicated to get the formula from, because it's all based on that charge ratio. So in order to figure out that ratio, we first have to know what is the cation and the anion that we're dealing with. And for our first example, our cation is ammonium. This is from our table on the side here. And so NH4 plus, ammonium, there we are. Phosphate actually occurs here as well on our polyatomic table, and it's PO4 with a charge of 3-. When we're getting our formula, we need to make absolutely sure that we have an equivalent amount of charge from the positive as the negative. And to fulfill that here, it's going to be NH4 3 to show that it's 3 ammoniums, therefore ammonium needs to be in parentheses. PO4 3- is its charge. We have one of them to go with 3 ammoniums to give us the neutrally charged NH4 3 PO4 ammonium phosphate. I would recommend this process for all of these, and even if you're doing it quickly in your head, you still should be able to define all of these correctly. What is the cation? What is the anion? And how do they both make an equivalent amount of charge in order to balance each other out, an equivalent positive to negative charge. Here are the following ions that hopefully you're able to identify. And when we have these ions, we get the following compounds, all of which now have an equivalent contribution of positive and negative charge. For our covalent species, things are a little bit different because it's not based on the charge, it's just based on the number. And so we do need to know our prefixes here, but when we know those, we see phosphorus pentafluoride, that's 1 phosphorus, penta meaning 5, so 5 fluorines, and we have PF5 is our formula for that. Carbon monoxide, same deal. We see carbon, we know it needs 1 oxygen because it's monoxide, and there's our formula CO. For the last question, we want to say, well, what's the key difference in chemical structure? And that's really the key to this problem, is that we do know that there's difference in naming conventions, but we want to go beyond just saying, well, we add the prefixes for the covalence. We really want to begin with the chemical structure and then talk about why the naming convention is really important for that structure. And for this, I would consult this picture. We have covalent molecules. So here is an example of 3 CO2 molecules, and we have an ionic structure which forms a crystal lattice as shown here. And again, the point is that when we look at the molecules, there's a specific number of each that makes this unit that's called a molecule. And those ones interact with each other in some way that we'll definitely talk about a lot later in the course. But for now, we really do need to recognize that there may be a ton of stuff in a single molecule, and there may be a small molecule like this. However, this idea that each unit is packaged into a molecule is unique to covalent compounds and not to ionic, which are shown here. We see sodium, Na+, chloride, Cl-, and they exist in a 1-to-1 ratio in this repeating network, and that ratio is determined by the number of each. And note that there is no molecule here. It's not like we have a single sodium and a single chloride that are existing as a pair apart from the rest. There is no distinction. They all exist together based on their ratio. So that's the difference in the chemical structure, very important, and it really sets up the naming differences. Because in covalent, it's definitely true that we do need to say the number of each, and therefore we state the ratio explicitly. And that's in contrast to ionic compounds, which is all about the charge. The charge determines their ratio, and that's how we name ionic compounds, based either on their charge explicitly given because it has to be, or an implied charge because it only gets one specific charge. Not even implied, but if it only has one charge that we get off the periodic table, then we know the charge, and we can just combine them and we'll know all about that ratio because we know the charge.